Hello everyone, I'm Rémi Goguet. I'm Senior Software Architect for the Data Center Business Unit at Kalray, and I will talk about Smart Storage Adapter for Composable Infrastructures. Before starting, a few words about Kalray at SDC. As you may have noticed, Kalray is well represented this year as SDC with 4 sessions. In this presentation, I will talk about Smart Storage Adapter for Composable Architecture. In a few words, the variety of architecture force to have both disaggregation and at the same time forcing IT to simplify data center by moving to hyperconverged infrastructure. However, we know that the HCI approach is based on software disaggregation and has a capacity waste and scalability issues. In this paper, we will describe how Kalray fully programmable MPPA Smart Storage Adapter and the NVMe-oF fabric offload server from heavy storage disaggregation task. A few words about myself before starting. I'm a senior software architect at Kalray. I have more than 25 years experience in the semiconductor industry and more precisely in embedded software with a strong expertise in system-on-chip, real-time operating system, voice over IP, and high-performance packet processing. In this presentation, I will start by introduce the challenge that data center providers are facing related to the infrastructure as well as the workload, the data-centric workload, and how the MPPA processor can solve it. Then I will describe more precisely the MPPA technology, the architecture of the processor, and the associated firmware framework. And finally, we will take the specific use case of hyperconverged infrastructure, show its limitation, show also how the NVMe-oF fabric technology can help, and finally, what do we propose with our smart storage adapter in order to totally offload the x86 server and move forward to a composable infrastructure. A few words about data processing. It's not new that we live in a data-centric era. Everyone agrees, and I won't give you a figure, some chart with ton of terabyte generated per second. It's not the subject of this presentation. We want simply to focus what does it mean in terms of data center workload and challenge. Basically, the scale-out approach in data center and the microservice-based application has four direct results. First, there is, of course, a network traffic explosion. It's not only the north-south traffic, but now we have a lot of east-west traffic because of microservice-based application, multi-tenant, and so on. Of course, we have the data storage capacity explosion as well. Data storage are spread across server. We are facing the disaggregation. It's not possible nowadays to have a full data set for an application to be stored in a single node. Another effect is a security threat. Because of the multi-tenant approach, cryptography is everywhere, and security is no more a question of data center boundaries. We have to manage security everywhere in the east-west direction, both in the storage and the network. And finally, we have more and more complex data processing. It's no more a question of packet encapsulation or firewalling, but we have now to perform some AI, some analytics about data flowing, and more complex processing. All those data-centric processing are generally performed by general purpose CPUs and OS, namely x86 in the majority of the servers. It's estimated that around 25% of the server is spent in data-centric computation, namely storage stack, network stack, and cryptographic conversion. And we all know that general-purpose CPU has been optimized and designed for decades with a single objective, is to execute user application, generally single-threaded application, as fast as possible. Therefore, they have out-of-order execution pipeline, there are complex memory hierarchy to hide memory latency, and so on. But they are not being designed at all to perform this kind of processing. The conclusion, and many of you will agree, I'm sure, is that there is a real need for a new class of processing accelerator to process this predominant data-centric processing task. Some of you are calling it data processing unit. I personally like this term. Some other will call it I/O processor, but at the end, this is the same. Regarding the data center infrastructure challenge, a quick word about the recent evolution of data center infrastructure. Data centers have many evolved in the past decades, from mainframe to converged infrastructure and now hyper-converged infrastructure. The goal is really to reduce the complexity and reduce the cost and increase agility and the scalability. At the same time, we need to have disaggregation, mainly for storage. There are larger and larger datasets generated by application and virtual machine, a large diversity of application workload, and we need to be as flexible as possible. And ultimately, we data center provider are seeking to reach a composable architecture where any hardware, whether it is a disk or SSD or a GPU, can be plugged into the system and expose new services to the other. The two first items, HCI and disaggregation, have been partially solved by a solution which is called HCI 2.0. which basically associate HCI and disaggregation. This is performed by software layers that run on top of HCI node, but increase the load on the CPU, increase the load on the HCI clusters, is complex and expensive, and limits the cluster scalability. And finally, HCI does not enable composability by itself. The second conclusion is that we really need a new approach to move forward to a truly composable infrastructure. Let's talk about the Coolidge MPPA right now. Some of hardware vendors try to overcome this x86 overload limitation by moving some more intelligence into their network interface card, NIC. They call it Smart NIC. Basically, the idea is to put a bunch of 8 cores, 8 to 16 cores, RISC cores, general purpose, in SOC, and to associate it with a data plane, ASIC data plane programmable pipeline. The problem is that the data plane programmability is really limited. It's not possible to add new services. It's not programmable in C. You can only perform processing for what it has been designed for. And as soon as it's out of the skills of the ASIC, the processing has to be performed by the control plane cores. Typically, as soon as you want to perform a TCP/IP termination, the CPU cores have to perform it by software, and the performance are limited. Kalray MPPA-free technology is totally different. We rely on a massively parallel processor array, 80 cores, VLIW cores organized in 5 clusters. Each core is programmable, whether it is used for management or control plane. For example, a cluster can be dedicated for a Linux operating system or control plane, or whatever it is used for data plane. The data plane can be 64 cores and totally programmable and perform any data plane processing, whether it is stateful or stateless, networking or storage, block processing, cryptographic, and so on. A quick look about the inside of the MPPA College architecture. From right to left, it's easier to explain. On the right, you can see the 5 clusters of the MPPA. They are connected each other by a ACI fabric and high-performance network on chip fabric. You have 2 Ethernet, 100 gigabit each, communicating to the cluster through the network on chip with a programmable load balancer and hardware packet parser, and 16-lane PCI and DDR connected to the ACI fabric. Therefore, each processor is able to send and receive traffic to the internet via the network on chip, or to access to the DDR or PCI via the ACI fabric. At the center, you can see the cluster itself with 16 processors. 16 cores are cache coherent inside the cluster. You have a large 4 megabyte memory, which can be used at TCM or L2 cache. We have also a high-performance microprogrammable DMA in order to communicate through the NOC or to the AXI. And also we have some cryptographic accelerators in each cluster. On the left, you can see the microarchitecture of our proprietary VLIW 64-bit core, 6 issue, with its MMU, its instruction and data cache, and an associated convolutional accelerator to accelerate deep learning operations. Let's have a look now about data-centric workload characteristic, the requirement for a performance data processing unit, and we will demonstrate that the MPPA College architecture totally fits those requirements. Data-centric workload characteristics are, the first one is a high parallelism. There are many stateless or stateful contexts, with, for example, TCP/IP termination context, TLS context, IPsec session, NVMe queues and associated block device layers. All are highly parallel. For this kind of parallelism, the many-core or MDMD architecture is the best choice. It cannot be executed on GPU, which are dedicated to run a single kernel in a highly parallel way. The second characteristic is a short temporal locality. With basically complex memory hierarchy, L1, L2, L3 are not well suited. It doesn't make sense to pollute the cache with a packet that will be processed only once. For this reason, it is preferred to have simple and deterministic memory subsystem and a large on-chip memory with high bandwidth, of course. The third characteristic is I/O intensive, with high IOPS and gigabyte second and a low latency. For this reason, with the data processing unit, will need an optimized interconnect, high bandwidth, low latency, and deterministic system on chip, and high-speed interface, of course. The fourth characteristic is a computational intensive. We will need AI inference, analytics, cryptographic, erasure coding. For this, we will need floating point unit, AI acceleration coprocessor, cryptographic acceleration, erasure coding acceleration. And last but not least, the main characteristic of those data-centric workload is a variability and the flexibility. We need to have a programmable data plane, whether it is stateless or stateful, and we need to use standard APIs and standard language like C and C++. MPPA College totally fits those requirements. We have this many core with 80 VLIW cores running at under 2 GHz, organized in 5 clusters. We have 20 megabytes of tightly coupled memory, and which can be used as level 2 cache or TCM. We have an hyper network on chip, 100 gigabit Ethernet, a PCI 16 lane Gen 4, high performance floating point unit, a high performance AI accelerator, and cryptographic accelerator, and we are able to perform line rate Reed-Solomon processing. Of course, we are based on standard API, and we leverage SPDK and Open Data Plane API as much as possible. Let's now talk about the Smart Storage Adapter solution and the associated software framework. Kalray does not only build processor, but also board. The MPPA-3 architecture is provided on 2 boards. One is in full haste and one in low profile. The board have, of course, the many core processor on it, high-speed interface, and can run NVMe-over Fabric stack, which has been certified by the IOL laboratory. We can drive advanced SSD using the PCI Gen 3 and our dual port SSD. The board can be configured either in standalone mode or in host CPU coprocessor. We have NVMe emulation, which allows to plug the board and to be used by any server which has the NVMe support. We have hardware accelerator on it and a low power. You can see on the bottom some key figures of the performance that we can reach for NVMe over Fabric target solution. Associated with this board, we provide the Access Core framework. The Access Core framework is based on open software environments, Linux and SPDK. The data plane is fully programmable, also with SPDK block device abstraction layer, and we can add network and compute additional services. For example, at 3 mega IOPS, half of the core are available, which allow us to put some storage service like erasure coding, RAID, dedupe, compression, and so on. Given the fact that we use standard API and protocol, the integration into a system is really simplified. On the network side, we use standard protocol like TCP and RoCE and standard NVMe over Fabric, which allows to communicate with any NVMe over Fabric appliance. On the management side, we provide a 1 gig management interface with Swordfish and Redfish support. On the PCI side, we are able to control any NVMe or SAS HBA because we have embedded Linux. And we are able to expose NVMe personality through the NVMe emulation layer. In this picture, we will see where does it fit inside data center appliance. First, it can be put in the FBOD or FBOF configured in standalone mode, which means that we don't need any x86 processor in those storage shelves. We can put the Kalray Smart Storage Adapter inside HCI storage or compute node with capacity, and we can put a Smart Storage Adapter inside x86 compute node without storage capacity. In this two later case, the adapter is configured in PCI mode and has some peer-to-peer capacity in order to control NVMe or SAS HBA peripheral inside the server. An example of typical usage of the storage adapter is a Lima JBOF that has been designed in partnership with Wistron. It's an optimized JBOF with no x86, and we can drive up to 24 U.2 NVMe SSD with 2 to 6 NVMe controller. Let's talk about the software now. SS Core Storage is fully programmability, efficiency, and use standard as much as possible. Programmability. We are fully programmable on both data plane and control plane, which means that on control and management plane, you can use Linux, typically one cluster, 16 cores. And on the data plane, we have a light OS, run to completion OS, that is executing the data plane and can use up to 64 cores. Efficiency, because we are running a run to completion full data plane from network function to NVMe stack and driver for IO queues. And we do true inline processing. There is no need for x86 pre or post processing. And finally, we are standardized because we provide standard hardware interfaces like NVMe emulation on PCI, and we leverage software API and toolchain from Linux, SPDK, data plane or open data plane and SPDK bidade, as well as acceleration library, we are ISAL compliant. Here you can see the 4 cluster data plane cluster and the control plane cluster. The Linux is running on the control plane cluster and cluster OS or proprietary light OS run to completion on 4 data plane cluster and all the interfaces. On the Linux cluster, you will find the SPDK application, basically for the control plane. You will find the Redfish Swordfish support via a port of Intel RSD PSME. And you will find the PCI interface, root complex, or peer-to-peer. If required, we are able to drive a SAS HBA through the standard Linux, and we are able to make a communication link very efficient in zero copy between the data plane and the SAS HBA using the new IO ring library API. On the data plane, we have cluster OS or light OS, which drives Ethernet and PCI endpoint. We rely on Open Data Plane, a standardized packet framework equivalent to DPDK, and we have third-party optimized network stack for TCP/IP termination and workload termination, for example. But also we are able to perform IPsec or TLS. On the storage side, still on the data plane, we are still on cluster OS. We are able to perform PCI endpoint for NVMe emulation, PCI root complex for SSD access, and we use SPDK block device abstraction layer as an API to provide some openness for storage services. The big picture with both control and data plane. The conclusion is a very complete and modular software framework. It's based on optimized SPDK for both data plane and control plane, and is open to partners. Let's talk about a specific use case right now, the future hyperconverged infrastructure. In the following slide, I will show you the limitation that we can have with a standard and current HCI infrastructure based on software. I will explain that adding NVMe over Fabric interconnect can help a lot, but is not sufficient. And finally, I will show you that using our smart storage adapter is a step toward a fully composable infrastructure. The typical current HCI topology is in this picture. We have HCI data silo in each cluster, and all the nodes are connected through a TCP/IP cluster interconnect. What happens when an application is created? It is created on one node with its data residing in the locality storage. After a migration, the application has to access its previously created data, and for this use the main TCP/IP cluster interconnect and the storage virtualization software layers. The result is an overload on the interconnect and overload on both CPUs, which have to perform its 86 storage stack and TCP/IP stack. After that, if new data are created, they are created on the physically running application node. The result is a fragmentation of data. Finally, to prevent interconnect overload, we have to move all the previously created data to the new running cluster node, which is not very efficient. The result is a series of storage, capacity waste because we have to over-provision, performance limitation, and fabric bottleneck. An intermediate solution is to add NVMe over fabric interconnect cluster. Using standard RDMA NIC to perform a ROCE, we are now able to provide a full data repository and to remove the ceiling. We can, since data are now global, are seen as local for nodes connected to the NVMe-off fabric, we can reduce some nodes with capacity or without. We can optimize the footprint and the cost, and we can even leverage some NVMe over fabric storage shelf like FBOF or FBOF. Now, what happens when an application is created and migrated? The application is created, you have migration, and now you have to access your previously created data. It's no more performed by the TCP/IP cluster interconnect, but by the ROCE interconnect. The result is that the TCP cluster interconnect load is not affected. That's a good point. However, we still have some load on the x86 because the x86 processor have to perform storage services and NVMe over fabric storage stack. The conclusion is that NVMe over fabric alone improves TCP/IP cluster interconnect, but not the x86 storage stack in efficiency. Now let's replace the RDMA NIC by Smart Storage adapter. The main difference by using Smart Storage adapter is that we are able to take full control over local NVMe or SAS adapter and expose those volumes, physical volumes, through NVMe emulation, which means that the x86 only use NVMe, local NVMe drive through the NVMe emulation function, and is not aware about the location of the data. Same scenario, application is created, migrated, but then since the application only sees local NVMe volumes, the Smart Storage adapter is in charge on NVMe to NVMe over fabric conversion, and then there is no server impact about the data migration. In conclusion, by offloading NVMe over fabric and storage service in the Smart Storage adapter, any volume is seen as local. There is no more need to perform data migration at all. Now let's have a look inside the HCI node. The HCI node will have some SAS drive, SSD or HDD, connected through a SAS HBA via the PCI bus. We'll have some NVMe drive, private for its own OS and boot, or for as a storage capacity for the cluster. The blue drive are totally controlled by the Smart Storage adapter, which means that the x86 cannot access it directly. Therefore, this blue drive can be accessed by the NVMe over fabric using the Smart Storage adapter, or by the x86 local by using NVMe emulation function. Typically, an access from an NVMe over fabric initiator to NVMe drive will be performed by the NVMe to OF to NVMe translation. Same for SAS HBA. We will have NVMe over fabric to SAS block translation. Access to a local SSD is still possible using the NVMe emulation to NVMe. And same for local access to SAS drive. We can see in this case that the NVMe-oF and storage services can be performed by the Kalray Smart Storage adapter, We can also add caching using a dedicated and high-performance Optane SSD. We can use distributed erasure coding, exposing no more physical volume but logical volume, NVMe volumes. And we can have high availability by performing mirroring between nodes. The conclusion: using smart storage adapter, we can go toward a true and efficient composable disaggregated infrastructure. You will have higher performance, and you will be able to exploit full NVMe SSD capabilities and offload x86 from heavy storage stack, like erasure coding. You will have lower cost because you are progressively switching to a true composable disaggregated infrastructure with commodity components, and you will optimize HCI node efficiency. It's still fully flexible. We still have a fully programmable data plane, and we are able to open the data plane to allow third party to have their storage service as required. And finally, we are future-proof because we leverage on standard NVMe-oF over Fabric protocol. We are compliant with other NVMe-oF appliances, and it's easy to update on the field. Thank you for your patience, and I appreciate your feedback.